Okay, so let's use the multiplication rule again, but we need to be concerned about whether events are independent or dependent, because if two events are dependent, when we look at how you multiply the probabilities, we have to multiply the probability of B given A if the two events are dependent, whereas if they're independent, we don't need to worry about this condition. So let's see this first problem. A coin is tossed and a single six-sided die is rolled. Find the probability of landing heads on the coin and rolling a 3 on the die. These two events are independent because the flip of the coin doesn't have any effect on what we'll get on rolling the die. So let's see. To get heads on the coin, there's two sides, so 1/2 is the probability of getting heads, and rolling a 3 on the die is 1/6. So multiplying those two probabilities, I get 1/12. In number 2, we've got our deck here. A card is chosen at random from a deck of 52 cards. It's then replaced, and a second card is chosen. What's the probability of choosing a jack and then an 8? So anytime things are replaced, my probabilities or my events are independent because the probability doesn't change. So what's the probability of choosing a jack? Well, there are 4 jacks out of 52 cards, and there are 4 8s out of 52 cards. So I could multiply these, but I could also reduce them first to get 1/13 times 1/13, or 1 over 169. In problem 3, a card is chosen at random from a deck of 52 cards. What's the probability that it is red and a queen? Well, here, red and queen are not independent events, so we're going to need to use this dependent rule. So the probability of red and queen would be the probability of red times the probability of a queen given that it's red. Okay, so what's the probability the card is red? Well, half of the cards are red, so 1/2. Over here, what's the probability it's a queen given that it's red? So if there are 52 cards, half of them are red, that's 26 cards. And out of those 26 cards, which ones are queens? Well, there's the Queen of Hearts and Queen of Diamonds. That's 2 of them. So if I multiply these two probabilities, I would get 1 out of 26. Or if I want to think about it, in that whole entire deck, 2 out of 52 cards are red queens, which is 1 out of 26. Number 4, a jar contains 3 red, 5 green, 2 blue, 6 yellow marbles. Marble is chosen at random from the jar. After replacing it, a second marble is chosen. What's the probability of choosing a green and a yellow? Again, because they're replacing it, the probability of choosing a yellow will not change from its original probability. So the probability of choosing a green times the probability of choosing yellow. So there are 16 different marbles. There are 5 green ones, so the probability of choosing a green is 5/16. And there are 6 yellows, so 6 out of 16th, and if I multiply these, I get 30 out of 256, which reduces down to 15 over 128. I think that might be able to get reduced further, but I'll just leave it there. In problem 5, let's tilt this, move this a little bit, excuse me. In a shipment of 20 computers, 3 are defective. 3 computers are randomly selected and tested. What's the probability that all 3 are defective if the first and second ones are not replaced? Okay, so when we do not replace, then again we need to be concerned about dependent events, so our probabilities would change. Tree diagram might help out in this case. So what's the probability that I get a defective one? Well, 3 out of 20 is the probability that the first one's defective. But now I'm only dealing with 19 and not 20. So how many out of those 19 are defective? Well, we had 3, now we only have 2 defective ones. So times 2 out of 19. And then if I continued on with my tree diagram to get that third one, now I only have 18. And how many are defective out of those 18? Well, just 1. So this is how I would multiply those. Again, the probability of getting a defective one changes as you keep picking without replacement. So if I multiply these cross, I end up getting 1 over 1140 after simplifying my fraction.